deviations above the mean, or above what we expected to see. That's a lot. But we have to be careful interpreting this in the t-distribution, because sometimes something like 6 may not actually be unusual. It depends. So what we'll resort to is interpreting the p-value. That stays the same. So again, we see that our p-value is really small. It has that e with a negative value at the end. So 1.6 e negative 9 is our p-value. So that means we have 0.8016. Okay, so without a doubt, our p-value is going to be less than alpha, which is 0.01. Since we have a really small p-value, that means what we've observed, seeing an average of 1265, would be extremely unusual if we expected to see 1200. Okay? So we expect to see the average of 1200. We saw 1265. That's 6.5 standard deviations above what we expected. So in other words, 1265, while it's only 65 hours away, is 6.5 standard deviations above 1200. Pretty unusual. And there's a very small probability that we would observe 1265. Okay, that's what the p-value is about. So since it's so small, from our flow chart from Thursday, that's telling us that what we've observed is unusual. We can reject the null hypothesis. It no longer makes sense. And we will support the alternative. So we just interpret that in terms of the problem. So at the 1% level of significance, the data do support. Now we just look at the problem and we pick out the question that's being asked. The data do support that the new process produces TV tubes with a longer average life. Okay. So you may note that we didn't use the value from the hypothesis. We didn't say anything about 1200. It would also be correct, and it's up to you how you want to do it, whatever is more natural to you, I suppose. Your conclusion could read something like, the data do support that the new process produces TV tubes with an average life greater than 1200 hours. You could also say the new process produces TV tubes with a longer average life than the old process, which had an average of 1200. You can word it multiple ways, okay? But the important thing is indicate the parameter that you're describing, either an average or a proportion, have your level of significance, and then indicate whether or not the data support that alternative. Okay? So, hypothesis test for means, new theory, new function, but the process stays the same. Okay? Glean the important information from the problem, get a p-value, compare that to alpha, make your conclusion. Example 8. A computer repairman believes that the average repair cost for damaged computers is less than $95. So in this problem, what we're measuring is how much does it cost to repair a computer. So that's something continuous. And the belief is that that average is less than $95. To test this claim, he randomly samples 7 computers. So right away you may notice that's not a large random sample, and that's okay. When we're analyzing means, it's not always necessary to have a large random sample. You can have a small random sample. That allowance to have a small random sample comes with an assumption. So if we have small samples, we have to assume that the population distribution, meaning whatever we're measuring, what does its distribution look like? It has to be normal. We're assuming that it's normal, or at least approximately so. So we're measuring repair costs for computers. Could that be normally distributed? Maybe. I mean, it depends. There is a limit at 0. It has to be bigger than 0. But I think it's reasonable to say that it's normally distributed. Okay. So we'll have to make that assumption as we proceed. From that sample of 7 computers, we found that the average repair cost, X bar, was $100 with a standard deviation, S, of 4250. At the 5% level, evaluate the repairman's claim. And here I tell you, I specify, assume that the repair costs are normally distributed. Okay. In the real world, you would have to understand that assumption and evaluate that assumption. For now, I will tell you whether or not you can make that assumption. So this mu less than $95, that's sort of what we're trying to show. So that's going to be the alternative hypothesis. The null hypothesis then is equals 95. They'll always have the same value. So once you figure out the value that goes in one of the hypotheses, you know the value for the other. They're always the same. Now, as we evaluate these data, we're trying to show that the average is less than 95. So we look at our information that we acquired from the sample, and we get an average of 100. So right off the bat, we're not supporting the alternative. We probably won't be able to support it. Our data, our evidence, is larger than 100. So we're not going to be able to support the alternative. We'll verify that with the p-value. So we have means, we're doing a hypothesis test, we're going to do a t-test. Alright, so we still have the stats. We believe that the mean is 95, sample mean of 100, standard deviation of 42.5, N of 7, and we think that the average has decreased. So take a second, make sure you typed everything in correctly. If anything is wrong by even a decimal point, your conclusions could completely change. What will really mess up your conclusions is choosing the wrong alternative sign. You have to pick the right sign. Picking the wrong one will likely completely flip your conclusion in terms of interpretation. So what we see, we get a p-value of 0.6169, and we'll go ahead and just round that to 0.617. 3 decimal places is fine, 4 is better. So the p-value, 0.617, and we always compare the p-value to alpha, which was 0.05. So what we see, the p-value is bigger than alpha. So if the null hypothesis were true, if we expect to see an average repair cost of $95, then there's about a 62% chance to see an average repair cost of 100 in a sample of 7. So it's pretty likely to see what we've seen if the true mean is 95. So since that's likely since we're likely to see what we've seen, there's nothing unusual. Our data are not unusual. We do not reject the null hypothesis. It seems okay. It seems reasonable that the true mean would be 95. So since we don't reject the null, we do not support the alternative. Okay. So in terms of the problem, we would say something like, at the 5% level of significance, the data do not support HA. The data do not support mu is less than 95. So in terms of the problem, the data do not support that the average repair cost for damaged computers is less than $95. Okay, can't do it. Our sample mean was 100. Let me see if I can get it focused there. Sample mean was 100, definitely not less than 95. They just don't agree with one another. So in turn, the null hypothesis makes more sense. We can't say, given these data, that it's less than 95. If we had more data, maybe that would change, but that's the case here. Okay, the last example, example 9. Example 6, I'll just post a solution for that. It's sort of a tricky problem. I'd rather go over it together sometime, just in terms of understanding the details of that experiment. A problem like that wouldn't be on the exam. It's difficult to think about, so I'll just post a solution to it sometime later. So example 9, we've seen this before with the confidence intervals. So this employment information service dealing with this very specific and detailed population, they claim that the mean annual pay is $24,600. And that's what they think. So to evaluate this, we have a random sample of 10 workers. So again, the problem just says full-time male workers without high school diplomas. My bad, I should have included over age 25, as one of you pointed out. So we'll assume that we're taking this sample from the appropriate population. Their average annual pay was $24,124. So close to the claim so far, not too far away. But we need to figure out not that it's $400 and some different. How many standard deviations apart are these? That's what we're really interested in. That's related to the p-value, which is how we make our decision of whether or not these agree or disagree. The standard deviation, 2629. And we're going to evaluate these data at the 10% level. So we're doing a hypothesis test. We're given a level of significance. We're going to assume that the mean is 24,600. So what's the alternative hypothesis? The problem doesn't say. It just says the mean annual pay, or they claim that it's 24,600. Evaluate that claim. If that's all the information you have, you just need to evaluate this, then we're going to try to show that that's not true, that it's something different than 24,600. Okay. So if no other specification is provided, it's a not equals. So we'll do a t-test. we believe that it's 24,600. Our sample mean was 24,124. Standard deviation was 2629. And the sample size was 10. Not equals. Hit calculate. So here we go. P-value is 0.58096, so we'll just call that 0.581. Okay, that is bigger than alpha of 0.1, so we're going to not support the alternative hypothesis. So at the 10% level, the data do not support that the mean annual pay